Only 3% of high-energy collisions at the LHC produce detectable supersymmetry signatures, yet 2026 could change that. A 2023 CERN study suggests hidden supersymmetric particles may decay into rare photon pairs, detectable by ATLAS. But your body's atoms, built from quarks and gluons, might hold clues to the same forces shaping the universe. In 2003, Nima Arkani-Hamed scribbled an equation in a coffee-stained notebook that could unify gravity and quantum mechanics. Now, with the LHC's upgraded power and new detection methods, that equation might finally face experimental validation or collapse. It took 23 years to build the machine to test it. Supersymmetry, born in the 1970s, now hinges on the LHC's 2026 upgrade. The universe's secrets may finally be within reach. In 1971, physicist Yuri Golfin proposed a theory where every particle has a super partner, a radical idea that would later be called supersymmetry. His work, buried in Soviet journals, resurfaced in the West in the 1970s, sparking a revolution. Giacomo Gerbier, head of CERN's LHC projects, recalls the 1990s debates. "We thought SUSY would be found by 2010. We were wrong. The hierarchy problem, the mystery of why the Higgs is so light, became SUSY's defining challenge. The universe is balanced on a knife's edge," says Arkani-Hamed in a 2020 Scientific American interview. The Large Electron-Positron Collider, closed in 2000, failed to find SUSY, but its data shaped the LHC's design. "We built the LHC to be 100 times more powerful," says Fabiola Giannotti, CERN's Director General. Yet even with the LHC's 13 TeV collisions, SUSY remained elusive. The 2012 Higgs discovery was a triumph, but no SUSY particles appeared. "We've narrowed the search, but not eliminated it," says James Gilliam, former ATLAS spokesperson. The European Strategy for Particle Physics 2026 upgrade. The hunt continues. From 2010 to 2018, the LHC collided protons at 13 TeV, a feat that once seemed impossible. ATLAS and CMS found the Higgs in 2012, but no SUSY particles appeared. James Gilliam, former ATLAS spokesperson, recalls the frustration. "We scanned every decay channel. Nothing. It was like searching for a ghost in a crowded room." The data from Run 2, while groundbreaking, left theorists scrambling. By 2023, the exclusion limits for gluino masses had climbed to 2.5 TeV at 95% confidence, a number that felt both triumphant and disheartening. "We've narrowed the search but not eliminated it," Gilliam admits, his voice tinged with the exhaustion of a detective who's followed every lead. Post-2012, the theoretical landscape shifted. Models like split SUSY and hidden valley SUSY emerged, reimagining SUSY not as a simple partner to every standard model particle, but as a fractured, shadowy version of itself. Katsuo Kabuki, former CMS spokesperson, explains, "We're not looking for the same SUSY as in 1975. The universe might be hiding it in ways we didn't anticipate." This shift mirrored the LHC's own evolution, no longer just a machine for brute force discovery, but a precision instrument probing the edges of the known. The European Strategy for Particle Physics Taiwan 2020 declared SUSY a priority, but not without skepticism. The LHC era must answer the hierarchy problem, the document stated, yet many physicists privately wondered, what if SUSY isn't the answer? The HL-LHC's 2026 upgrade, with its 10x higher luminosity, was framed as a last-ditch gamble. Giacomo Gerbier, head of CERN's LHC projects, acknowledges the stakes. "This isn't just about SUSY. It's about whether the standard model is enough, or if we need something more." As the machine hums toward 2026, the question lingers. Will the data finally crack the code, or prove that the universe's deepest secrets lie elsewhere? The HL-LHC's power isn't just in its numbers, it's in its precision. By 2026, its 10x higher luminosity will mean 150 300 FB minute of data, a volume that could finally tease out the faintest whispers of SUSY. "This is our best chance," says Fabiola Giannotti, her voice steady as she walks the control room at CERN, where engineers fine-tune the upgraded beam optics. The old LHC was a brute force machine. The HL-LHC is a scalpel. The upgrade's heart lies in its detectors. ATLAS and CMS now boast pixel sensors with sub-micron resolution, capable of tracking particles that decay in trillionths of a second. For gluinos, predicted to weigh 110 TeV, their decay into quarks and neutralinos would leave telltale jets of energy, a signature that, if seen, would be a smoking gun, as Nima Arkani-Hamed once put it in a 2021 lecture. Neutralinos, the dark matter candidates, would manifest as missing energy, a ghostly absence that theorists have been hunting for decades. Their decay signatures are subtle but detectable. Arkani-Hamed insists, scribbling equations on a whiteboard during a 2023 seminar. We've been looking in the wrong places. The HL-LHC will change that. Yet the data alone isn't enough. Atlas and CMS have allocated 30% of their 2026-2035 data taking to SUSY, a decision driven by the European Strategy for Particle Physics, which declared the hierarchy problem the defining challenge of the LHC era. This isn't just a scientific gamble, it's a philosophical one. If SUSY is found, it would validate grand unified theories, stitching together the forces of nature into a single elegant framework. This would be a Nobel moment, Arkani-Hamed says, his eyes alight with the same fervor that drove him to propose SUSY in 2003. But the stakes are even higher. If the HL-LHC's data reveals not SUSY, but something else, a new symmetry, a hidden dimension, a flaw in the standard model itself, then the universe has just rewritten its own rules. And that, Giannotti adds, is why the world is watching. The HL-LHC's detectors, now armed with pixel sensors capable of resolving tracks at submicron precision, will scrutinize every collision for the faintest traces of SUSY. These upgrades are like giving the LHC a pair of glasses, says Giacomo Gerbier, his hands gesturing at a 3D model of the Atlas detector. We're not just looking for particles, we're looking for patterns in the noise. The machine's beam optics, refined through years of trial and error, will now steer protons with unprecedented accuracy, ensuring collisions occur in the precise regions where SUSY signatures might emerge. Meanwhile, algorithms trained on decades of LHC data will scan for anomalies, gluinos decaying into quarks, neutralinos escaping as missing energy, or supersymmetric particles popping into view like ghosts in a fog. If SUSY exists, it will show itself in the data, insists Nima Arkani-Hamed, his voice tinged with the same urgency that drove him to propose the theory in 2003. But it won't be obvious. It will require patience, creativity, and a willingness to see the world differently. The European Strategy for Particle Physics framed this as a scientific gamble, but for physicists like Fabiola Giannotti, it's a moral imperative. We've built this machine not just to confirm SUSY, she says, her gaze fixed on a control screen displaying the HL-LHC's progress. We've built it to ask the universe the hardest question: what are we missing? As the first collisions of 2026 approach, the world holds its breath. The answer, whether SUSY or something stranger, will not only validate a theory but redefine the very fabric of reality. And in that moment, the chalkboard will no longer be a battleground of equations but a portal to the unknown. The human story of SUSY is one of relentless pursuit of a theory that once seemed tantalizingly close, then vanished into the noise of data. Fabiola Giannotti, now CERN's director, recalls her own youth. I remember sitting in a lecture hall in 1995, hearing a physicist say SUSY would be discovered by 2010. I believed it. I needed to believe it. That dream, shared by generations of physicists, now hangs on the edge of 2026. For Giannotti, the HL-LHC isn't just a machine. It's a testament to the patience of those who built it, the courage of those who believed, and the humility of those who may have to accept that SUSY isn't the answer. Science is about patience, she says, her voice steady. Even if the data doesn't confirm SUSY, we'll have pushed the boundaries of what we know. If SUSY fails, the next chapter of physics will be written by others. Katsuo Kabuki, who once led CMS's SUSY searches, now leans toward axion models or extra dimensions. The standard model might be more complete than we thought, he admits. But that doesn't mean it's all there is. The search for dark matter, for the quantum nature of gravity, for the unification of forces, these questions remain unanswerable only by SUSY. Philosophically, SUSY's legacy is a mirror. Is the universe a hologram, as some string theorists suggest? A quantum computer, as others propose? The data from 2026 may not answer these questions, but they will force us to ask them again. As Nima Arkani-Hamed once said, we're not just testing physics, we're testing reality itself. What if the LHC's 2026 results rewrite the laws of nature? The universe is not only stranger than we suppose, it is stranger than we can suppose. If this journey through the mind of a genius left you thinking, subscribe and hit the bell. Tell us in the comments which theory keeps you up at night.